Okay, or how can I, okay. I would present our study of the real-time TD-DFT study of the Spin-Phonon dynamics and some application to band topology and something high harmonics. The title sounds luxurious, but I think we are specifically we want to study the light matter interaction in the DFT framework. I schematically shows the light impinges on solid or molecule as you see here. And to do this job, we have developed the real-time evolution of the DFT. And this is we show the TD-DFT, the time-dependent Quantum equation, including the light field as a vector potential. And sometimes we include the classical vibration and the vibrating or the oscillating scalar potential, the originated from the classical vibration. So by this, including this atomic vibration through the scalar potential, we can describe the electron ion interaction, and this light vector potential. We can include the time oscillating for example, the monofrequency or the pulse frequency, pulse light. And the consistent time evolution for the quantum wave function and the density can be well accounted by a few algorithms currently called Noah-Strict-Roto. And we are basically interested in the solid state, so the periodic boundary condition of the scalar potential is well implemented by this the plane wave and pseudo potential package. And the electron correlation is treated up to Hubbard model, and the spin-orbit coupling is also modeled. And so that the quantum wave function can be scalar or the two-component spin-or depending on the physical situation. And from the time evolution, by calculating this time-dependent wave function, time-dependent quantum orbital, we calculate some physical quantity like charge current or the spin current. So let me show you one specific example why we need to calculate and when we studied by using this computation result. And by developing this computation method, I would say that we are more interested in the low frequency, the insulator dynamics driven by low frequency. Low frequency means that the kind of photo-electron system. I think most of study have studied the electron excitation or the kind of excitonic phenomena. But we are at this time, I think we are more interested in the solid state excitation by low frequency light, the frequency much below than the band gap. So for example, suppose we have a insulator. This is band structure, and the insulator, the magnetic anisotropy. In this case, the spin is directed in plane. In this case, the spin is directed out of plane. This insulator spin configuration can be controlled by optically or phonon. By controlling phonon, we are interested in this type of example. For example, this is a kind of a well-known two-dimensional ferromagnet, chromium I3, and by applying a light pulse of the frequency 2.5 electron volt, we can TD-DFT calculation, we can obtained the change of a spin anisotropy direction in the 1 picosecond. So this is one example what we can do by this computation. And this two-dimensional magnetic system, the magnetic anisotropy has a kind of a significant, very important physical meaning that can be it originated from the very old paper, but the effect of geometry and the symmetry on the magnetic order. But today I would skip this part. And also we can calculate the effect of a very strong field on the insulator. And one of the effects of a strong field is that the nonlinear response or high harmonic response. So today I just show you this real-time evolution can be applied to this type of phenomena. I would like to, in this presentation, I would like to focus on two of a specific example of our recent study. One is that this real-time evolution can be applied to the calculation of block band topology. Here, again, the insulator by calculating the Berry curvature. And the other example is that the Spin-Phonon Ehrenfest dynamics calculation. And we show that the one example that the circularly rotating phonon can provide the features of a time reversal braking, something very similar to the absorption of a circular photon. So I would present these two specific examples in this presentation. And this is references. Let me start by the very well-known textbook material. This is the original paper published by the Professor Michael Berry in 1984. This is the first introduction of a Berry phase. Berry phase is in this original paper, the Professor Berry motivated to formulate, to derive answer for the shape of the solution of the time-dependent Schrödinger equation, especially when the Hamiltonian changes through a parameter RT, and provided that we have a time-independent Schrödinger equation, what will be the solution of a time-dependent Schrödinger equation? And the Berry's argument is that the time-dependent, the solution of a time-dependent Schrödinger equation mostly similar to the instantaneous time-independent solution, but there should be additional phase. This additional phase is called the Berry phase. So the Berry phase is a very general concept, and the Berry phase can be represented by the line integral of the Berry vector potential and something like a magnetic vector potential. The curl of vector potential is defined as a very curvature, like a magnetic field. And this very curvature is a very important, one of the most important concept in the solid state physics, because in the solid state, the expectation or the electron flow in response to applied bias, the Berry curvature produced the so-called anomalous velocity. So I depict here, suppose for example, if we have some solid material and if you apply the static bias, then it will not exactly follow the bias. It will deflect if there is a significant Berry curvature present in the solid. So the Berry curvature is kind of a it acts as some kind of internal magnetic field. So one of the very simple example can be provided by this 2x2 graphene model, and also the the graphene band structure and the cones, Dirac cone-like band structure is very well known. So the near the cone Fermi point, the 2x2 linearized Hamiltonian can be modeled this way, and so by diagonalizing the 2x2 Hamiltonian, we can calculate the graphene band structure. But this band structure, when we can assume that the very weak electric field, very weak electric field is applied along the x direction, so that we can think of the block point evolving along the Brillouin zone. And when the block Hamiltonian time evolve this way, we can think of a time evolution of a block state and adiabatic evolution of energy eigenvalue. This is our calculation, and by this adiabatic evolution, the eigenvalue, you can show that eigenvalue follow the line of a static eigenvalue. But what the various theorems suggest is that on this adiabatic evolution, the eigenvalue evolve along the line of a static eigenvalue. But the wave function, there should be additional phase. This is the very phase. And as I showed you 2 pages before, this very curvature will be reflected as on the anomalous velocity. And so by calculating velocity expectation, we can derive the Berry curvature, and also by calculating by this calculating the velocity or the current, we can derive the Hall conductivity. When the current y direction current is generated in response to the x direction bias, the coefficient is called the Hall conductivity. In the same way, we can calculate the spinor conductivity. I will show you the example later. So this Hall conductivity is the very important significance in the history of the integer quantum Hall effect or the topological state. The very seminal, the most important starting paper is published in 1982. They showed that the insulator, two-dimensional band insulator, the Hall conductivity is quantized. The Hall conductivity of 2D band insulator is quantized. So the proportional integer is called the Chern number. So this is the kind of the two-dimensional band insulator contains the intrinsic quantum Hall effect, and we will show you that by calculating the velocity itself, we arrive at the result of the Chern number. So the TD-DFT calculation can be utilized to the calculation of this Chern number. This is the very famous model Hamiltonian, 2x2 model Hamiltonian, that introduced the kind of a time reversal broken state, the Chern insulator model. And by calculating the time evolving state, for example, let me show you that the band structure, we can by making the sweeping, the blow vector sweeping over the Brillouin zone, we can reproduce the band structure of the various phases of the Haldane model. And also not only the band structure, this is the static calculation, but you see that this is the kx static calculation, but this is the time-dependent calculation. We calculate the band structure, but not only energy eigenvalue. This is a static calculation of Berry curvature, but we calculate by calculating the velocity. We can calculate the Berry curvature, and the integration of the Berry curvature, integration of this velocity, we arrive at the Chern number to indicate, to quantify the Chern insulator. Well, this is a demonstration of the concept why the time evolution technique can provide the classification, the topological state, the Chern number state. But this concept is useful for the real material by performing the real-time evolution of the TD-DFT by applying the electric bias onto this external potential. And for example, when we apply static bias on graphene, this is the static calculation of Berry curvature, and this is the whole velocity calculation obtained by the real-time evolution of the TD-DFT. So the whole velocity of the electron at the k valley and the whole velocity of the electron at the k prime valley is very well produced. And